So here we're asked to sketch the Fourier transform of the function that was defined in part D. We're not actually asked to calculate the Fourier transform, we're given the result here. So this is the function that we're expected to sketch here. Now if we look at it, it looks very similar to the sinc functions that we met in the lectures. The only difference is both the sine function and the denominator are squared. So this is a sinc function squared. So the prefactor to the sinc function is going to tell us about the amplitude of the sinc function when the argument is 0, and then the functional part is the sine and the denominator. We can see that the argument of both the sinc function and the denominator is omega tau divided by 2, so we'll use that as our variable. So we can draw some axes. Now because it's a sinc function squared, the function is never going to be negative. We can mark on some suitable points, pi, 2 pi, and also minus pi and minus 2 pi. We know that the sinc function will go to 0 at integer multiples of pi. So just like a normal sinc function, the sinc function squared is going to be non-zero at 0, and so we can draw the point there, and then it's going to come down to 0 at pi. Unlike a normal sinc function, because we're squaring it, it isn't then going to become negative. It's going to do this. It's going to stay positive, and we're going to get it as even function, and so the function has to do this as well. The amplitude at this point here, again, it's the prefactor, so that's tau squared divided by the square root of 2 pi. And again, we can label the horizontal axis. This is w tau omega tau over 2. So this is what the function will look like. It looks like the sinc function, except because we square it, the bits that are normally negative become positive.